Harlan Stenn, and I work at Network Time Foundation and on the NTP project. I wanted to say hello and thank you for inviting me here. Today I'm going to talk about the network time protocols, plural, and a little bit about Network Time Foundation. There we go. Have you ever had to debug a problem that involved a remote system? If you have remote access, you can watch both sides of what's going on and see when things happen. If you cannot see both sides, you have a chance if each side displays enough information so you can correlate events. If you have to work with another person on the remote side, that adds another layer of complexity. If the analysis is happening after the fact, then correlating and understanding is much harder unless the events have correct and accurate timestamps. This is the core mechanism of how NTP transfers time. A client sends a packet to a server, and T1 is the time when the client transmits that on the wire. And that is taken, T1 happens on the client's clock. When the server gets the packet, it records the time when the packet arrived as T2, and it records the time it sends its response as T3. T2 and T3 are based on the server's clock. Finally, when the packet arrives back at the client machine records T4 according to its clock. Simple, huh? Here's an example of how the math works. If the client and the server have synchronized time and their clocks are running at the same speed. I'm not going to spend too much time on these slides because if any of you really care, you can download the presentation and study the slides at your leisure. In this example, the client and server's clock are running at the same speed, but the client's time is behind the server's time by 10 seconds. And as you can see, the math works out so the offset actually gets reported as 10 seconds. And we can see that there's a total network delay of 2 seconds here. 1 second to get from the client to the server, and another second to get from the server back to the client. This is a difficult situation because the client's clock and the server's clock are running at different rates. The good news is that over time, the client will keep slowing its clock rate down and will eventually synchronize with the server. The different rates of the two clocks are why the calculations look a little funny, because they're based on time data from clocks that are running at different speeds. Theoretically, in reality, NTP requires clock rates of the systems to be within 500 parts per million of each other, and this example is 2,000 times worse than NTP can correct. So if this situation was actually in place, the client would eventually give up and not even try to synchronize with the server. So we can take what we've learned to do so far and build on that. What we learn next is how we can use the information from these time transfer volleys to adjust the clock so it follows the time source. To see if the client's clock and the server's clock are running at the same rate, we just do another NTP packet volley, learn the time offset and network delay, wait a while, and do it again. The client knows how much time passed between the two volleys, and it knows how much time passed from the server's point of view. If the two values match, the clocks are running at the same speed. Otherwise, the client knows the rate at which the client's clock differs from the server's clock. Here's an example of how we can figure out the rate difference between the client's clock and the server clock. In this case, we see that 100 seconds after the first NTP volley, the client's clock is off by 1 millisecond. It also means that the client's clock rate is different from the server's clock by 10 microseconds per second. For the client to match the server, the client just updates its clock to first account for the time offset, the 1 millisecond time offset, and then the client also has to adjust the speed of its clock by 10 microseconds per second to make its clock match the rate of the server's clock. The amount of time between volleys is called the pole interval, and NTP sends its volleys at this rate to best determine how to adjust its local clock to keep it synchronized with the server. And this has been a basic overview of how NTP and time transfer works, and how the information it provides is used to synchronize the clock's time and rate. The information in the packet volley also gets us the network delay from the client to the server and then back from the server to the client. We need the network delay value because when the client adjusts its clock, the time adjustment is the sum of the calculated offset plus 1/2 of this network delay. If the network delay is asymmetric, that asymmetry will introduce a bias into the applied offset correction. Let's look at another wrinkle, the packet's transmit time. You can see that T1 and T3 represent packet transmit times. T1 is when the client sends its request to the server, and T3 is when the server sends its answer back to the client. Here, we know that the clock get time call gets us the time, and then it has to return this value to its caller. This takes a little bit of time. Next, the program stores that value in the packet, which takes a little bit of time. And finally, we call the send function to actually transmit the packet to the other side, which also takes a little bit of time. Authenticating packet content increases the reliability that the time we got in the packet is actually correct. This is usually done with some sort of checksum. To calculate this checksum, you have to know the actual data, which means the time we're trying to send. So the processing time to get an authenticator into the packet adds more delay between getting the time and sending the packet. We can note the difference between the transmit time on that first line of code there and the time the actual packet is sent, which is the clock get time call at the end. But this difference is actually a little bit too long because a little bit of time passes between the send call and then getting the time after which. I'm not going to go into details here, but there are several ways to get corrected packet transmit time sent around and send that information to the other side. So how do we communicate the time? That gets done between the time source and the current computer, and also with the remote system, so we can exchange time. There are always going to be trade-offs here. In these next few slides, I'll talk about some of them. In the old days, modems and phone lines were much better for time transfer than networks for synchronizing clocks. NIST, the National Institute of Standard and Testing in the USA, used their Automated Computer Time Service, ACTS, to closely synchronize time between their master time sources and their satellite offices. They were able to increase their pole interval to between a week and a month at a time. So instead of sending an NTP volley every 100 seconds, they would send them once a week or once a month. Remember, NIST is the legal source of commercial time in the USA. They constantly measure and monitor time at their locations. They soon learned that back then they could synchronize clocks using modems and the public switch telephone network much better than they could if they just used the network. Technological advancements and improvements come with trade-offs. While soft modems and digitized telephone networks provided many benefits, these benefits came at the cost of losing a great way to synchronize time. The same trade-offs also happened with LAN technology. Some reference clocks are sources of time, provide a pulse at the stroke of each second. This is called a pulse per second signal. I recall that Dave Mills and the Sun Solaris driver engineers put a lot of work into the Sun Solaris NTP Streams serial terminal driver, so it could use an RS-232 serial stream for accurate time synchronization. Their kernel driver code had big warnings about how, if anybody needed to make changes to the code, they should check with the NTP Streams engineering team. Of course, From time to time, some other engineering team would decide that they needed to make changes to this code, and they would release it without telling the NTP streams engineers. And then there would be support calls logged because the NTP streams performance broke. Much hardware these days no longer comes with real serial ports, and most folks are happy with USB serial adapters. The problem is that going directly from a real serial port to I/O that happens off of a pulled serial USB connector adds even more jitter and decreases the time quality. So technology advancements come with costs and benefits. There are consequences and trade-offs. Imagine small portable devices that have well-synchronized time over Wi-Fi. Half of the network delay tells us the one-way distance between the two systems. A delay of 3.3 nanoseconds is 1 meter of distance in difference between the two systems. So if half of the network delay is 330 nanoseconds, that means the devices are 100 meters apart. If we can learn the distance between all the devices in our group, we can map the possibilities of where all the devices are. Some GNSS, the global network satellite systems, are optimized to report time, and others are optimized to report their location. Since I looked at this nearly 20 years ago, advancements have clearly been made, and I would not be surprised to learn that the drone light shows that you can now see are using technology that relies on these concepts. NTP keeps the time in the heart of the kernel. As that time gets moved from the kernel to other layers of the system, jitter happens. The more layers, the more jitter we have. PTP, on the other hand, keeps time in the clock on the edge of the network card. If there is a simple cable that connects one PTP network interface card to another, PTP can synchronize the time very well. But to do anything useful with this time, one has to move it from the PTP clock at the edge of the network interface card into the kernel, and from there out to user space. Every one of these moves adds jitter. Here's a picture. Yay! Finally, we got some pictures. I hope you can see the little clock on the outside edge of the NIC. You can see that pretty much nothing gets in the way of transferring time between the two PTP NICs. Having two systems with PTP NICs directly connected offers the best time transfer, but that's usually not an effective way to operate. But there are steps to transfer the time from the clock on the NIC chip to the heart of the kernel, and from there to anywhere else time is needed. In each of those steps, jitter is added. There's no such thing as a free lunch. And just because it bears repeating, jitter happens whenever something is touched or moved. This slide tells a bit about how NTP was designed to synchronize time. Under really great conditions, NTP can synchronize time about as well as PTP can. It takes a lot of work, and it's expensive, but it can be done. Here's the similar picture from NTP's point of view. You'll notice that there is no clock in the network interface card as far as this model is concerned. PTP was designed to transfer time over a bus, and as folks got more familiar with the technology, they were able to use PTP to transfer time over a local area network. A PTP network must be very carefully designed and deployed. PTP switches cost much more than normal switches. Again, there's no such thing as a free lunch. Regardless of the protocol used, noise and jitter get added at most every significant operation. To summarize, NTP is designed to transfer time at the network level, and that includes in space, over a wide area network, or over a local area network. NTP can usually easily synchronize clocks on a LAN to the sub-millisecond level. PTP, on the other hand, was designed to synchronize time and the clocks on a bus, Over time, folks learned how to do this over a LAN, given proper design, equipment, and network conditions. Here's a basic diagram of a PTP network. On the left, you have a PTP grandmaster that provides the time. It sends it into a PTP-capable switch, which then sends the time to PTP client 0, and from PTP switch 0 to PTP 1, and then from PTP switch 1 down to PTP client 1. As I mentioned, PTP switches cost more than regular network switches, and in order to have good performance, a PTP network must be well and properly designed and operated. If clocks disagree, then the out-of-sync clock must have its time converge with correct time. If the environment is bad enough, it might take NTP a week for this to converge, but it will do the job. While a warm start NTP client can synchronize to the server in about 8 seconds time, if the client is doing a cold start, and also we have to determine the frequency difference, it can take much longer for the clocks to synchronize with the remote server. PTP can cold start and get synchronized within a few seconds, but to do this, it must send hundreds of volleys per second, behavior that is not allowed by the NTP specification. NTP and PTP have different use cases and require different operational environments. Given enough time and money, NTP can get very close to PTP performance, and PTP can get very close to NTP's performance. Here's a fun story. There was a master time lab that ran for years, and the way it worked was they'd power the thing up. While it was starting to boot, the server clock would synchronize with the time source, and by the time the server came up, it was ready to serve correct time to its users. And one day they decided to replace their public-facing server, and that new machine powered up much faster than the old machine. And since it got its time from an accurate source, it didn't have the correct time when it was ready to serve time to the public, and there were a few seconds where it decided to tell everybody it was the 1st of January 1970. That's slightly after midnight. For the next story, NIST, the National Institute of Standards and Testing, is about a mile away from University of Colorado Boulder campus, and they stretched an optical underground cable between the two places so they could help each other do experiments. On a hot day, the length of this cable grew by about 11 millimeters, which is less than half an inch. They have to monitor the temperature along the cable run and account for this difference, because on a hot summer day, that mile-long cable gets about a half-inch longer, which means that it takes 0.05 nanoseconds longer to travel that half-inch. And you can see how many zeros that is and how it affects time just from the slight expansion length of that cable. Since this was done in 2011, clocks have gotten much better, and they can measure these differences now over much shorter distances. I did want to mention a little bit about Network Time Foundation and what we're doing here. Over the years, I've learned that time is important and pretty much nobody wants to pay for it. I also learned that if there was no organization or legal entity that focused on these things, if somebody did want to support our work, there was no place they could send money or equipment. So I initially thought about creating an NTP foundation and immediately realized that focusing only on NTP would be too narrow. For example, PTP is also in a similar situation, and those projects need equipment and money to get their job done. So in 2011, I started Network Time Foundation to offer an organization that was dedicated to support open source network time projects. A couple of quick thank yous I'd like to make. There's 3 people there: Laura Jones Crothy, who helped me with the slides, and just to say it, I really like the music of Pedro Aznar and Tanya Maria, and I don't think any of them will ever know I feel this way. I just wanted to say it, and there are a whole lot more people I could mention. Finally, if anybody's interested, here's a link to the Mills Spring Fund. Dave Mills started the NTP project back in the early 80s, uh, developed the first, with several other people, developed the first releases of NTP, and then I joined the project in probably the early 1990s and worked with Dave until he died earlier this year. So Dave and I have a history that goes back over 30 years, I believe. If anybody's interested, please visit the Network Time website or the NTP project website and check it out. That's what I got. Thank you very much.